All right, I actually pressed record this time. Um, so last time we talked about singularities, removable singularities, poles, and essential singularities in preparation for the residue theorem, which we're going to talk about next week, and that'll be the last thing we talk about. Um, Forgot to record that lecture, so I'll have to go back and do that. So if you're watching on YouTube, then I apologize. Hopefully that won't take me too long to do. But anyway, today we're going to take a detour into Fourier analysis. And we're going to start by talking about periodic functions. Oh no. There we go. So a complex number, let's call it omega, is called a period of some function f if f of z plus omega is equal to f of z wherever f is defined. And if this omega is not zero, we say f is periodic. All right, no surprises so far. So as an example, we have the exponential function, the complex exponential function, which is periodic with periods 0 plus or minus 2 pi I plus or minus 4 pi I, and so on. And we have the complex exponential with an I in the argument, which is obviously also periodic, but um, the periods are 0 plus or minus 2 pi plus or minus 4 pi, and so on. Now, sums of periodic functions, guess what? They're periodic. Right? If I have f and g and they're both periodic with the same period. So with the same period. If I have two functions f and g which are periodic with the same period, if I sum them, I add omega, the period, to the argument, well then they're both periodic, and so they both reduce to just the functions evaluated at z. So this tells us, for example, that the cosine, which is e to the iz plus e to the minus iz over 2, and the sine function, which is e to the iz minus e to the minus iz over 2i, these are both periodic with the same period as the exponential functions. Okay, so one of our goals today will be to show that any periodic function, I should say any periodic analytic function, in a half plane or strip can be represented as a sum of exponential functions. Okay. So one thing we should note is that if the period omega is non-zero, then this new function g of z, which we define by f of omega z, is periodic with period 1. Right? This is because g of z plus 1 is f of wz plus w, which is f of wz, which is just g of z. Okay, so let's go ahead and focus on functions with period 1, which are analytic and a horizontal strip. So I'm picking a horizontal strip just to have something concrete to work on. So we come to our first theorem. If f is analytic on the horizontal strip, alpha less than imaginary part of z less than beta, so that looks like here's alpha, let's say, here's beta. It's this horizontal strip between these horizontal lines. And let's assume it's periodic with period 1. Then f can be expanded as f of z as a sum from k equals minus infinity to infinity of ak e to the 2 pi I k z, where we again assume we're in that horizontal strip. And this series is absolutely convergent. And in fact, it's uniformly convergent on any substrip. So if I take a beta naught, which is maybe here, and an alpha naught, which is maybe here, then on that strip between those two lines, we have uniform convergence. Okay, so here's the proof. Let G be defined by G of e to the 2 pi I z equals f of z. So first of all, this is well defined, right? We have a little bit of ambiguity here because we can add factors of 2 pi I to the argument of the exponential here. But since f is periodic with period 1, we have we have g of e to the 2 pi I z plus 2 pi I is, well, that's g of e to the 2 pi I z plus 1, which is f of z plus 1. But by the periodicity of f, this is f of z, which is g of e to the 2 pi I z. Right. So this ambiguity and how we write this exponential function, it doesn't matter. This function is indeed well defined. And moreover, it's analytic, right? It's composed of analytic functions. Then this is for its domain. So this horizontal strip gets mapped to the annulus, e to the minus 2 pi beta less than magnitude of omega less than e to the minus 2 pi alpha. Now, since it's analytic in this annulus, it has a Laurent series. We expand g of omega as a Laurent series. So let's say it's sum over k, ak, omega to the k. So when I write omega here, I'm thinking of g as a function of omega. Okay, and this holds in the annulus. And so by subbing omega equals e to the 2 pi I z, I get the series I want. And this represents f. So that's all I need. And we can do the same thing. So we started out with these horizontal strips. We can do the same thing with a half plane. And the proof is pretty similar. So I'll assume the same things, F analytic, this time on the half plane, which looks like imaginary part of Z greater than alpha. So if we want to sketch that, maybe this is alpha here, then this is the half plane we're talking about. And F is periodic with period 1. If F is bounded as the imaginary part of Z goes to infinity, then F can be expanded as, again, the same thing. It can be expanded as, well, actually, this time a power series rather than a Laurent series. This is for the imaginary part of Z greater than alpha, so the half plane. And again, this guy is absolutely convergent. And it's also uniformly convergent in what I'll just call a sub half plane. So again, what I mean by that is if I choose another alpha which is inside of this half plane, then the half plane above that, like so, the series converges uniformly in. Okay. Proof. So, well, it's basically the same. So in this case, the change of variable omega equals e to the 2 pi I z that we used before. It maps this horizontal, not horizontal, the half plane, not to an annulus, but to a punctured disk. And now F being bounded, as imaginary part of Z goes to infinity, tells us that G is bounded as omega goes to 0. And so this tells us by Riemann's theorem on removable singularities that G extends to be analytic at 0. So what's happening is we have this boundedness criterion, which is telling us that the singularity we have at 0, right, because we're defined on a punctured disk now, that singularity is in fact a removable singularity. And so we can just go ahead and define the function there, and it becomes analytic. So this means that G has a power series. So not just the Laurent series, but a power series, G of omega. And this holds in the entire disk now. Okay, and so again, we just plug back in for omega, and we get the representation of F that we want. And so this completes the proof. Okay, so let me go ahead and move on to talking about Fourier series now. So by a Fourier series, maybe I'll say complex Fourier series. All I mean is a sum of the form sum from k equals minus infinity to infinity of ck e to the I k theta. So if we have f, which is analytic in an annulus, right? It has the Laurent series. Let's write it f of z equals sum from k equals minus infinity to infinity, ak z to the k. This series converges uniformly on the circle. This converges uniformly on the circle of radius r for some r. Um, and this will tell us that f of r e to the I theta, this is the same r as that one, is equal to the sum from k equals minus infinity to infinity, ak r to the k e to the I k theta. And this is the Fourier expansion of the function f of r e to the I theta viewed as a function of theta. Right, so we're defining some function of theta here, which we're going to go ahead and call the Fourier expansion. We're defining some function of theta here, which is represented by this series, which we're calling the Fourier expansion. Okay, so the Fourier coefficients are ck equals ak r to the k, and we'll have something to say about this in a moment. Actually, that moment is basically now. So suppose we have such a series. Which converges uniformly to f of e to the I theta. So I'm setting r equal to 1 here. We can recover the coefficients by noting that the sum, not the sum, the integral from minus pi to pi of e to the I j theta, e to the minus I k theta, d theta over 2 pi. This is a pretty easy integral to do. This is going to be 1 when j is equal to k and 0 otherwise. And that tells us that the integral from minus pi to pi of f of e to the I theta e to the minus I k theta d theta over 2 pi is equal to, I'm going to expand f and then take the summation out. So this is the sum from j equals minus infinity to infinity, cj, integral from minus pi to pi, e to the I j theta, e to the minus I k theta, d theta over 2 pi. And now I use this orthogonality result for these exponential functions, and this becomes ck. And so we have this nice integral expression for the Fourier coefficients, which we call the Fourier transform, but the Fourier transform is never actually mentioned in the book, so, to my surprise. So I'll stick with the language they used. Okay. So we have a couple of questions now that arise, such as, well, when does the Fourier series converge and what does it converge to, and so on. So let's address those. If f of e to the I theta is piecewise continuous with Fourier series f of e to the I theta, roughly something like sum over k. I'm going to need a ck here probably. E to the I k theta. Then for mn greater than or equal to 0, so any choice of positive integers, we have the sum from k equals minus m to n, ck modulus squared, plus the integral from minus pi to pi of the modulus of the difference between f of e to the I theta and this partial sum of the Fourier series squared. This is equal to the integral from minus pi to pi of the modulus squared of f of e to the I theta. Okay, so we're going to go ahead and prove this, but this is going to give us an inequality. We're gonna move this guy to the right hand side and get an inequality for the sums of the moduli squared. So the L2 norm basically of the Fourier coefficients, and that's going to be called Bessel's inequality. But let's prove this result, which is a little stronger. So let's take a look at this modulus squared of the difference between the function and the partial sums of the Fourier series. So this is f of e to the I theta minus the partial sum. So the modulus squared is equal to the number inside the modulus times its complex conjugate. Times the complex conjugate, which I'll denote with the overbar. So this is ck bar. And now e to the minus I k theta. Okay. So now we just multiply the product and integrate both sides from minus pi to pi. And what we find is that the right-hand side of this guy is given by minus pi, integral from minus pi to pi, modulus of f of e to the I theta squared d theta over 2 pi. So that's this term times this term being integrated, minus sum. I'm going to drop the indices for a second to save some time here. Over 2 pi, so that's this term times this term being integrated. And then we have the additional term, sum over Cj, integral from minus pi to pi, f of e to the I theta complex conjugate, e to the ij theta, d theta over 2 pi. It's this term times that term. And then we also have the sum of, well, the partial sums of the moduli squared, partial sums of the Fourier coefficients. Okay. And what we observe is that, well, this integral here is the coefficient ck, and this term here is the coefficient cj complex conjugate. And now when we put these together, we get modulus of Cj squared here. And so this term will cancel with this one. And so what we're left with is this guy. So this thing here, integrated from minus pi to pi. So that's this term is equivalent to this guy, which appears here, minus the the partial L2 norm, I'll call it. So this term is this guy here. And so that completes the proof. Okay, so the theorem tells us that the partial sums of the thing that I keep calling partial sum of the Fourier coefficients, or the like partial L2 norm, or whatever you want to call it, this thing is bounded. Right? That's what this tells us. And as a consequence, the L2 norm, or the sum of the Fourier coefficients, or the sum of the moduli squared of the Fourier coefficients, actually converges. And moreover, we get the following corollary, which I'll state as a theorem because it's used so much. It's called Bessel's inequality, which we get just by moving this term to the right-hand side by subtracting and then throwing it away to get the following inequality. So this is under the same assumptions as in the previous theorem. Okay, so the L2 norm of the sequence of Fourier coefficients is bounded above by the big L2 norm of this function f of e to the I theta, which is associated to the Fourier series. Okay. So I'm going to go ahead and prove our main result now out of the Fourier series sections. Let me go ahead and state it precisely. Suppose f of e to the I theta is piecewise continuous with Fourier series f of e to the I theta, which looks something like sum over k ck e to the I k theta. If f of e to the I theta is differentiable at theta naught, then the Fourier series of that function converges to f of e to the I theta naught at theta equals theta naught. So in other words, f of e to the I theta naught can be written as the sum from k equals minus infinity to infinity, ck e to the I k theta naught, which we note is the limit as m and n go to infinity of the partial sums. Okay, this one takes a little bit of effort to prove. We will consider first the special case theta naught equals 0, and then we'll reduce the more general case to this. So let's go ahead and tackle this case first. So this is the case where e to the I theta naught is then equal to 1. Let's define a function which is given by the difference quotient, f of e to the I theta minus f of 1, which is the value of e to the I theta at theta not equals 0, over e to the I theta minus 1. The differentiability f e to the I theta differentiable at theta naught implies that g of e to the I theta, which is this difference quotient, has a limit as theta approaches theta naught, which is, we're assuming, 0. So consequently, this g of e to the I theta guy is also piecewise continuous. And we can denote the Fourier coefficients of that function by bk, so that what we have is g of e to the I theta is, I don't want to write equals, I want to say it's related to its Fourier series. Right? We don't have equality yet. Like so. Now, Bessel's inequality, the thing we got right before this, tells us that, so Bessel's inequality tells us that these coefficients bk go to 0. This is as k goes to plus or minus infinity. Now we can compute the ck's. Compute the ck's in terms of the bk's. How do we do that? Well, we say since f of e to the I theta equals g of e to the I theta times e to the I theta minus 1 plus f of 1. That's just the definition of g, where did I write it? Up here. It's the difference quotient solved for f of e to the I theta. Okay, so since this is true, we have ck must be equal to the integral from minus pi to pi, g of e to the I theta, e to the I theta minus 1, e to the minus I k theta d theta over 2 pi, plus we have this extra f of 1 term. Okay, so basically we're taking the Fourier transform of both sides. When we express the integrals as Fourier coefficients, what do we find? Let's see. What we find is that ck will be equal to bk minus 1 minus bk if k is not 0. And c0 equals b minus 1 minus b0 plus f of 1. And so what this tells us is that the series, the sum over k of ck, telescopes. And what we obtain is the sum from k equals minus m to n of ck must equal f of 1 plus the sum from k equals minus m to n, bk minus 1 minus bk, which is f of 1 plus b minus m minus 1 minus bm from the telescope. And what I want to say about this, I want to say this tends to f of 1. as m and n go to infinity. Okay, and this proves the theorem for the case. So this, so therefore, theorem holds for theta naught equal to 0. Okay. So the case when theta 0 is arbitrary is reduced to the special case theta naught equals 0 by a change of variable. So consider the function h of e to the I theta defined by f of e to the I theta plus theta naught, which is related to the Fourier series sum over k ak e to the I k theta, and is piecewise continuous and differentiable at theta equals 0. The Fourier coefficient ak of h of e to the I theta is ak equals the integral from minus pi to pi f of e to the I theta plus theta naught e to the minus I k theta d theta over 2 pi, which is equivalent to integral from minus pi to pi f of e to the I k phi. I'm doing a change of variables here. Which itself is the Fourier coefficient ck e to the I k theta naught. So what this means is that the Fourier series of f of e to the I theta evaluated at theta equals theta naught is the sum over k of ck e to the I k theta naught, which is the sum over k of ak. And this is the same as the Fourier series of h of e to the I theta evaluated at theta equals 0. And we've shown that this latter guy converges to h of 1, which is f of e to the I theta naught. And so that completes the proof. Okay. So that's about roughly as far as Gamelin goes into Fourier analysis. It seems like an introduction. It's kind of a weird one because never actually mentions the words Fourier transform. It doesn't really go into great detail. He obviously proved some very important results that establish the theory, but doesn't go much further than that. He does prove in that section some identities or some results about doubly periodic functions that we already proved, I think, in an exercise in an earlier lecture. So I excluded those. But okay, any questions?